Hello and welcome. In this video, we're going to be doing our notes for projectile motion. Remember to pause or rewind the video as needed. Let's begin. As far as definitions are concerned, a projectile is an object that is under the influence of gravity. In other words, anything that gravity causes to curve once it is fired. Okay, so a rocket taking off into space would not be a projectile because the thrusters are causing it to accelerate upwards. Okay, but a ball flying through the air is curving because gravity is making it curve. The trajectory of a projectile is the path that the projectile takes. Okay, so example, if a bullet is fired from a gun and a bullet is dropped from the same height at the same time, which will hit the ground first? So you have two objects. One is dropped, one is launched horizontally. Well, the trick is they both hit at the same time. Both are pulled down by gravity. I'll demonstrate this one for you in class. That means that the X and Y motions are independent of one another. Okay, now to solve projectile motion problems, here's what you're going to have to do. You're going to have to make two charts. Now, recall, for a constant velocity concept, we made a list that looked like this. Delta x, v, and t. It was only three variables. Very simple. When you had a concept such as constant acceleration or even free fall acceleration due to gravity, you made a list of six variables, either delta x or delta y, v, v naught, a, and t. So you had a list of five variables. Well, the way this works is in all cases, acceleration in the y direction is due to gravity. And if you remember from our free fall acceleration unit, the acceleration due to gravity, all things will drop at a rate of 9 meters per second every second. Now, in many cases, this gets rounded up to 10. In fact, almost always it gets rounded up to 10. However, if you are doing labs or something more specific that involves this value for acceleration, you'll leave it as 9.8. The acceleration in the x direction is going to be 0. And the reason why is we're assuming that there is no air friction to account with. So there's no acceleration in the x direction because we ignore air resistance. Air resistance is like air friction. Think of it this way. If you had a wind blowing, if you had a ball flying through the air and you had a wind blowing it forward, that's adding velocity to it's adding a push. It's giving a push to your object flying through the air. If you had a ball that was flying through the air against the wind, it would be resisted, right? So we're assuming at this level of class that we would ignore air resistance. Now, in other higher level physics classes like AP Physics C or any other college level physics classes, there are units in the class that do involve air resistance and the calculus-based applications that you would apply to deal with air resistance. At this level, we're going to ignore it. So the acceleration in the y direction is negative 9.8. Sometimes this is also referred to as little g, right? 9.8. The acceleration in the x direction is called it's 0 because again, there's no There's no push. There's no net force in the x direction. So that's what happens. Now, when we're dealing with projectile motion, you're going to make a list of a total of 8 variables. Horizontally, we move with horizontal constant velocity. That's what HCV stands for, because you're not accelerating in the x direction. Therefore, horizontally, we have delta x, v naught, and t. But I'm going to say v naught in the x direction because I now have the x direction of my velocity I have to account for. Now, vertically speaking, you have to account for vertical motion too, because x and y are happening together, x and y motions, but they're happening independent of each other. So I have horizontal constant velocity and I have vertical free fall acceleration because objects are falling because of gravity. So I will list my free fall acceleration variables. Delta y, v, b naught, a, which is going to always equal negative 9.8 meters per second squared, and t per time. These times will be the same. The time it takes to fly through the air horizontally is the time it takes to fall or rise from the ground or fall to the ground. So when we do a projectile motion problem, we will make a list of 8 variables. Okay, so 3 for constant velocity, 5 for constant acceleration, 8 total variables for projectile motion. Let's see how all that works. Case 1. Projectile fired horizontally with an initial vertical speed v naught y equals 0. Okay, now there's really just two equations you're going to need. You're not going to need very many equations. So horizontally speaking, if you're moving with constant velocity, the only equation you'd use is x equals v naught x times t. It's your constant speed equation. Now, vertical free fall acceleration is going to require 2 different equations. One will be vy equals v naught y minus gt. This is going to be handy to find the vertical component of velocity as a function of time. Now, the other one you'll need is delta y equals v naught y times t minus 1/2 gt squared. Okay, now let me explain what I did in these equations here. In fact, actually, let's just go ahead and keep it similar to what we did before. And we'll just call this A. Keep it consistent. So 1/2 A and 1/2 A. And just remember, when we're putting in A, A is going to be negative 9.8. Sorry to confuse you guys. Okay, so for vertically speaking, I'll use one of these two. Horizontally speaking, I'll always use that. So there's only 3 possible equations we'll use for projectile motion. So it says a ball is thrown horizontally off a cliff with a speed of 12 meters per second. That makes that v naught x. V naught y equals 0. Why does v naught y equal 0? Because you're launching it horizontally. You have no velocity in the y direction. Off a 20-meter tall building. Okay, so here's the building. Delta y is going to be negative 20 meters. Why? Because it's falling 20 meters from 0. If you rise, your displacement is positive. If you fall, your displacement's negative. How long? We're looking for time. So what would I use? Well, if I'm trying to find time and I have displacement, I'm probably going to use that equation there. So delta y equals v naught yt plus 1/2 a t squared. Well, v naught y is 0. 0 times time is 0. So this whole middle term is going to cancel. And it leaves you with delta y equals 1/2 a t squared. Now, in order to solve for time, that's how long, you have to get rid of the a, the 1/2, and the squared. So let's begin that process. To get rid of the 1/2, Go ahead and multiply both sides by 2, and we get 2 delta y equals AT squared. To get rid of the A, we can divide both sides by A, and I get 2 delta y divided by A equals T squared. The last step to get rid of the squared to get T by itself would be square root both sides. Now, if you remember, this is the same equation we used to calculate your reaction time for your reaction time lab, dropping the ruler through your hand. Same equation. Let's go ahead and plug into it. 2 times -20 divided by -9.8. Notice the negatives cancel, right? And I'm going to go 2 times 20. The reason I'm not worried about the -20 because the negatives, they cancel each other, so I don't worry about them. So 2 times 20 equals divided by 9.8 equals, and then I have to square root that. Square root, um, try that again. So 2, so okay, 2 times 20 is that divided by 9.8 is that, and then I'm going to go square root of 4.08, roughly. So I'm getting about 2.02, a little over 2. 2.02 seconds it takes to fall. Okay, and then how far from the base of the buildings it land? How far would be delta x? That's this distance here. How far? Well, there's only one equation with delta x in it. That's easy. It's your v naught x times t. So how far? It's going to be v naught x times t. So it's going to be your 12 that you launched it with, 12 meters per second times 2.02 seconds. And we're looking at about 24.2 meters. Case 2. What happens when you have a projectile fired at an angle? Like a soccer ball kicked from the ground and it launches and lands. Now, it can launch and land on the ground. It could land on the roof of some building. It could be launched from a building and land on the ground. There's a variety of ways that you can have an angle projectile problem. But let's look at the information given. It's kicked with a speed of 20 meters per second. That's my V naught. At an angle of 15 degrees above the horizontal. That's my theta. Find the maximum height. Okay, so that's going to be, if you think about it, that's going to be my displacement at the time it takes to be at its highest point. So if I find the time it's in the air, if I find the time to, let's see, so it's the time to reach maximum height. I'll show you a couple ways we can pull this one off. And then horizontal distance, right? We're looking for delta x again. So the first thing we have to do is split V naught. So if this is my V naught, I have to split it into my horizontal component and my vertical component. There's my theta. Well, the blue component is the adjacent side of the triangle, V naught x. Well, that's just going to be your hypotenuse, V naught, times the cosine of the angle. My red component, my vertical component, that's V naught y. That's going to be my hypotenuse V naught times the sine of the angle. So I'm going to find those two values. This is going to be 20 sine 15, and this is going to be 20 cosine 15. Okay, let's figure those out. 20 times the sine, oops, erase all that. 20 times the sine of 15. Okay, about 5.18. Okay, when you find V naught x, same thing. I'm going to go 20 times the cosine of 15. And I'm getting about 19.3. Okay, now how am I going to find these things? So there's a couple ways I can pull this off. Okay, I can find the time that it takes to get to the highest point. So first, find time to reach the top. Now, at the top, we know that the vertical velocity is equal to 0. Why? Because what's happening here is the vertical velocity does this. It starts off very high. That's your initial vertical velocity. And as you get higher, the vertical velocity is getting smaller until Vy at the top is 0. Then the vertical velocity starts getting larger the other way. Okay, why is it 0 at the top? Because you're changing directions at the top from going up to going down. So Vy, velocity in the y direction, has to be 0. Well, that's helpful because I can use Vy equals V naught y plus AT, and I can solve for the t it takes to get to the halfway point, the top, using that as 0. So I will go ahead and subtract V naught y from both sides. And negative V naught y equals AT. Divide by A. And the time it takes to get to the top is negative V naught y over A, which is negative V naught y was 5.18. 5.18 meters per second over negative 9.8 meters per second squared. Okay, we'll throw that in the calculator. 5.18. 5.18 divided by 9.8. And I'm getting 0.53. 0.53 seconds. The negatives cancel. So that's helpful. Okay, now I can use the following. To find maximum height, just find the vertical displacement all the way to the top. I could use two different equations. I could use this equation, Vy equals, or delta y, excuse me, equals V naught yt plus 1/2 at squared. If I do this, there's more to plug in, but I can still do it. V naught y would be 5.18 times the time it took to get to the top, 0.53, plus 1/2 times negative 9.8 times 0.53 squared. Well, to take care of this, I would do this part first. I would do each part separately. So 5.18 times 0.53 is 2.75. So this part is 2.75 meters. Plus a negative means you're going to subtract, so minus. Then I'm going to go 0.53 squared times 9.8 divided by 2. 0.53, whoops, clear that. 0.53 squared times 9.8 equals divided by 2. And I'm looking at about 1.38. Subtract those. 2.75 minus 1.38. Whoopsie. Is about 1.37. So at that small angle of 15 degrees, it only gets barely up to about almost 1.5 meters high. Now, to find horizontal distance, oh, before we do that, sorry, one other way you can find max height is using this other equation, delta y equals, it's the fourth constant acceleration equation, and it's vy plus v naught y over 2 times t. We know that Vy at that highest point is 0. We know V naught y is 5.18. So if I go 5.18 divided by 2 times time, right, I'll have it. So 5.18, oops, divided by 2 times the time of 0.53. And you can see I'm getting 1.37. Okay, notice this way is a little bit quicker and easier to use, but honestly, this equation is not too bad either. You just need to plug in more things. To find the horizontal distance, delta x, we're just going to go v naught x times t. Well, v naught x was, what was it, 19.3? Times that time through the air, 0.53. So we'll go 19.3 times 0.53, and we're looking at about 10.2 meters is how long it's flying through the air. Okay, so the kind of an example, one example from each type of projectile problem. This is called a horizontally launched projectile, and this is called an angle projectile because it's launched, well, from an angle. So a couple things we should know. Number one, acceleration is negative 9.8 at all points along the trajectory. So if this is my projectile, the acceleration A is constant all the way down. At the lowest point, highest point, anywhere along, it's going to be that value. Okay, why? Because that is the rate at which objects are slowing down on their way to the highest point, and it's the same rate as objects are speeding up from the top of the highest point. The velocity is tangent to the path. Okay, what I mean by that is if this is your trajectory like this, then your velocity is going to look like that. It'll just be tangent to the path. Time depends on the vertical motion, and time is the same, right, for this. So time depends on the vertical motion, right, because Vy, right, is V naught y minus gt. So the vertical motion and time, right, they are dependent on each other. And the farthest possible distance for any projectile would be 45-degree angle, halfway to a right angle. All right. I hope you found these notes to be helpful. Again, they will make more sense in context when we do the practicing class together. Thank you.